I'm going to talk about building ITER and what we have learned. So the first thing is what is ITER, but maybe you know by now. So this is what we want to demonstrate, the scientific and technical viability of fusion energy as an energy source. So how do we want to do this? We want to build a tokamak that operate large unoperated, and our target is to have 500 megawatts of fusion power heating the plasma with 50 megawatts for at least 5 to 10 minutes, and then at a lower power of 400 for about an hour. And so this demonstrates, I would say, the part which is the physics of the fusion reactor and also the control. So you are able to control the reaction, you are able to control the discharge over a very long time scale, much longer than any time scale. And then we have to demonstrate key technologies. And these are the ones that were mentioned, that some of them have very low TRL, like heat exhaust, superconducting magnets, tritium processing, plasma heating, etc. And one important thing of ITER is that ITER is a public project, and therefore it is essential that we share the acquired knowledge among the ITER members. So the ITER members have actually access, the governments have access, and the public research institutions to the IP generated by ITER by law. It's not something we can prevent. We have to give permission, but we cannot say no. So you have to be authorized because you can use it for whatever, but we cannot say no. It's written in the ITER agreement. Now, it is an international organization, so it's made by 7 members, one of which is the European Union. And the peculiarity of this organization is that actually the members provide the components, as Ide-san has shown. 90% of the components are provided by the ITER members. So this means that, to my knowledge, we established the first worldwide supply chain for fusion. And of course, this is not simple. It's not simple because it's the first time you do it, and you can see that, for instance, for the toroidal field coils, and I will show a map because it's also very interesting to see geographically, but there were 6 ITER members involved. For the poloidal field coils, there are 3, central solenoid, and these are just the main components of the machine. And this means that you have to have, transfer of material from one to another. You have to have multiple factories providing the components. You have to have control of interfaces. But of course, a plant of this type is not just the tokamak, it's also the infrastructure around. So you have to have a large cryogenic plant because we are using low temperature superconductors, so we need a very large cryogenic plant. We have to convert the altered current at high voltage to low voltage continuous current. So at the end of the day, it is actually something here. ITER is the installation of the tokamak is something like this in this 40-hectare thing. And all these components that are there, not only the tokamak, are also provided by the ITER members. So we have transformers, power supplies, rectifiers, cryo plants coming from all over the world. The cooling plant was built by India and came here. The cryostat was built by India. And then some of the components are so large that you cannot actually transport them. So we had to set up a factory, which is this cryostat workshop. This is a high precision welding facility to weld the largest vacuum vessel of the world that provides high vacuum. And the PF coil winding factory, this is like 3 football grounds. This is where the PF coils were built by Europe because they couldn't be transported. So this is, you can see that of course this thing takes time to set up and also takes time to all the ITER members to get coordinated. There is many discussions, many meetings. And it took a while to get it right, I have to say. At the beginning, we had lots of misunderstandings, lots of problems, and I think now of course, we have the organization was set up in 2006. We started, the site itself started in 2007, so we have now 18 years of experience. And this is the tokamak itself inside the building. So you have to have actually, one of the issues that happens with fusion is that it's a nuclear system, but actually a very complicated nuclear system. On that side, you can see the building where the tritium is reprocessed, that it was mentioned yesterday, and on this side, you have all the measurement systems, that there are a lot. We have 60 measurement systems to measure 100 parameters, because it is an experimental reactor. Now, the lessons learned. So one very important thing is that the design must be sufficiently developed before construction starts. These are very large projects that take a long lead. So you actually, in many cases, and I think this is natural, you cannot have the design fully completed for everything before you start building, because if not, you will never build. So you have to start at some point. But one of the things we learned is that you have to do it sufficiently. For instance, in our case, one of the problems that we had is that because the components are provided by the ITER members, some of them are built to what we say, and some of them you get functional specifications that you have to fit here. For instance, one of the things it happened was that when we were starting to build the building, suddenly people realized that we have to have to know all the attachments of all the components of ITER, of all its life, which is many years, to set some plates in the building, because in the nuclear regulation in France, you cannot actually make a hole on the wall of a nuclear building. It's forbidden, because it creates cracks if you have an earthquake. So this means you have to embed a plate on the rebar before you make the building, and suddenly, in like few years, you have to set up the location of 200,000 plates. And this was something which was completely unexpected, because people more or less have interfaces, designs, etc. But suddenly when you say, where are you going to hold this? Nobody has thought in detail the precise location, and suddenly, so this was one of the problems. And there are many things of this type that you start, you think you have a design, and you have it, it's true, but when you start to build, you start to realize that the design is not well enough defined, and this is a problem. And another thing is the nuclear licensing aspects, because people do the nuclear licensing. Of course you do the nuclear licensing. This is natural. But then, people, for instance, because you don't have the design finished to the level, the maintenance requirements are not defined. And suddenly you find out that you have something in a place that you have to change every 3 months, and you cannot access. And so this type of things, to have a project developed to a level that you are sure of these things is essential, because then this is what happened to us. Fixing it backwards is a lot of effort. And suddenly you have crises, and you have to stop contracts which are ongoing. The companies, of course, charge you a lot of money because they are building, and you have to stop for a month because you have to solve it. Then another thing which is very complicated is the establishing, because here we are in the first of a kind. So for instance, the production of the superconductor we use for the toroidal field coils, which are made by Europe and Japan, and the central solenoid, which is done by the US and Japan. I mean, the coil itself is done by the US, the cable comes from Japan. The production has to be increased by a factor of 10. And this is one of the things that was mentioned. You have to give certainty to the companies that produce this. That is worth, increasing your manufacturing capabilities. Also, for instance, you need to water cool all the vacuum vessels, because you have very large plasma fluxes, etc. And before, these things existed in kind of this size. There were laboratory tests, etc. And suddenly you have to have 1,000 square meters of this. And this is not simple, and this is what Ide-san said, this you don't really find in the shelf of anybody. Nobody has this. So suddenly you come to an industry that has done some demonstration from some experiment, and you say, yes, this is very nice, I want 300 square meters of this. And you have ever produced maybe half a square meter. So this is something which is was quite a challenge to set up this change. And also, just to give you a complication, this is one of the coils which actually I don't know if it is made by Japan or Europe, this one, but you can see 70 meter tall, it weighs 9 meter wide, it weighs 300 tons, and this is the path in the world of the components of these coils. So you can see that, of course, all of them end up in a harbor near Marseille, but production took place all over the world. And this, of course, by the way, with the COVID, this was a problem, because all the sea navigation got very distorted, and we had some issues there. And this is why distributed manufacturing needs efficient logistics, because if not, you get stuck. At some point, particularly with the COVID, there were no ships, and the components were built, and they stayed in the countries, and they could not be sent. Also, one thing which is very peculiar of fusion is that you build very large components. Companies are used to build very large components, but you need very high precision. These things are built to millimetric precision. For instance, the poloidal field coils that were built by Europe, which are like this room more or less, they are plain to 1 millimeter. And they have to be, because if not, the magnetic field you produce is not symmetric. And if the magnetic field that you produce is not symmetric, you cannot increase the pressure. And then you cannot produce fusion, because the fusion goes with the pressure. So there is a strong We have companies that build large components, but they are not used to the precision of fusion. And I said this large-scale fusion supply was kind of difficult to set up. And now, other thing that we have is that when you do the prototype development and manufacturing, one of the things you have to test your component. And actually, the facilities that test the component are not simple. The facility itself, if you want to put something to test, for instance, the first wall of ITER, which is the divertor, which has to handle power similar to the surface of the sun, there are not so many places in the world where you can actually produce these fluxes. So actually, the acceptance test of the component becomes a task. It's not that you produce it and you get it, no. And okay, another thing which is very important is effective feedback loop with the providers. As the sun said, this understanding. When people find difficulties, they come back to you, you come back to them, because if not, you get stuck. People get stuck with the problem, they don't tell you, you don't know what is the problem, and so this openness is essential. And for instance, one of the issues that we had, because we didn't keep good quality control, is that in the process to produce some of the thermal seals of ITER which shield the coils from the heat of the vacuum vessel and the plasma, cleaning of the components were not properly done. Actually, we develop corrosion in these components. So this means you have a leak of helium into your cryostat, you cannot actually cool the coil. So this meant that after we have actually assembled one of the sectors, we have to take it out. And this is something which is quality control is essential. And when you have distributed production, you have to have quality control everywhere, because you do a mistake, and the consequence in our case was 2 years. Okay, and then I finish. So another thing that we have learned is this thing of the component. We have to learn to put the component. This is something that we know how to do, but it was not trivial. You have to put very large and heavy components with millimetric accuracy. So we can actually position these coils with 0.5 millimeter accuracy over 90 meters now. But this is something we have to learn, and it took us quite a lot of time. And also one thing which is quite interesting is that there are many companies that work in nuclear industry, which are the typical ones you would use to assemble these machines. But actually, we need high vacuum, which is the typical thing that they do in the space industry. And these two things don't exist together. People from the space industry, they know how to get things very clean, but people from nuclear industry, they do not. So we have to put them together. No, because if not, your vacuum vessel is very dirty and you don't actually get a discharge. So there are many of these things that, I think when you go to small scale to large scale is when you realize, and this is one of the things we have learned in ITER, that we have to take attention to this. Now, finally, we learned, and I think things are going pretty well, but we had a difficult time because of this.
Well, thank you, Alberto.